Welcome to Probability Video 2, Probability Trees and Bayes Theorem by Elizabeth A. Albright at the Nicholas School of the Environment. This video will talk about probability manipulation with trees, and we will walk through a shellfish problem solving with a tree and Bayes' theorem. I'll also provide a practice problem on oil drilling. As you may remember, I presented a problem in Probability Video 1 about shellfish harvesting in the estuaries of North Carolina. I asked you to read through the problem to identify the marginal, conditional, and/or joint probabilities that were given, as well as the probability that the problem is asking you to solve. If you have not watched Video 1, I encourage you to do so. If you have not written down the probabilities given in the problem, I ask you to stop the video now to write them down. As discussed in the previous video, there are marginal and conditional probabilities presented in the problem. Please stop the video and check your work to make sure it aligns with the probabilities listed on this slide. If it does not, I encourage you to go back to Probability Video 1 and review the solution to the question posed. The question that the problem asks is the probability that fib exceeds the standard given the shellfish is contaminated, right? This is a conditional probability, but it was not given in the problem, right? We are asking for a kind of a flipped probability, but we can solve this with the probabilities given in the problem, either through the use of probability trees or through the use of Bayes' theorem. Here we have a probability tree which allows us to sketch out the uncertain events and outcomes in our problem. The nodes represent the uncertain events and the branches the outcomes and associated probabilities with those outcomes. We will work through the tree from left to right. The green events are conditioned on the outcomes of the first event, the orange node. The orange node and branches that come from it represent the marginal probabilities. They are not conditioned on the outcomes of any other events. We can calculate the joint probabilities by multiplying the marginal and the conditional probabilities. Please stop the video and sketch down this probability tree. You don't need to write down the words associated, just the structure. So here's our probability tree, and we can now start filling in the probabilities associated with each of the uncertain events. So marginal probabilities that were given in the problem. We have fib exceeds the standard. That equals 0.10. And fib does not exceed the standard. That equals 0.9. And those two marginal probabilities should add up to 1, should sum to 1. Now we can add in the conditional probabilities. Probability that shellfish is contaminated given or if the fib exceeds the standard is 0.75, and shellfish not contaminated given fib exceeds the standard is 0.25. The two branches or all of the branches off of a given node should always sum to 1, so we are good there. And we can fill in the final two branches. Shellfish contaminated, given fib does not exceed the standard, is 0.05. And then we know this final probability is 0.95. So we have the marginal probabilities and the conditional probabilities that were given in the problem. We can now calculate the joint probabilities, which we know is the product of the marginal and the conditional probabilities. So we just multiply straight across. 0.1 times 0.75 equals 0.075, 0.025, 0.045, 0.855. And we know that all of the joints, those four probabilities in this case, should sum to 1. So please stop the video and fill in your probability tree to look like this. So the problem gave us the probability that shellfish is contaminated given fib exceeds the standard. We can think of this as P, or the probability of B given A, seen there on the probability tree, 0.1 and 0.9. But we want to know the probability of A given B, probability that fib exceeds the standard given shellfish contaminated. And so what we want to do is flip the tree, or flip that conditionality. So we can do this either through probability tree manipulation or through Bayes' theorem. So what we want is to do the first step, which is calculate the marginal probability of shellfish contamination. The marginal probability is the sum of the two joint probabilities that include shellfish contamination. So the probability of shellfish contamination equals probability shellfish contamination and fib exceeds the standard plus the probability of shellfish contamination and fib does not exceed the standard. Right? It is the sum of the two joints that both contain shellfish contamination. We can look back at our original tree to find these joint probabilities. And we need to remember that probability of A and B equals the probability of B and A. The ordering in joint probabilities does not matter. This is our original tree. And you can see the four joints on the right in blue. And I have starred or dynamited the two joints that we need to sum together to calculate the probability of shellfish contaminated. So probability of shellfish contamination down below there equals 0.075 plus 0.045, which equals 0.12. We could sum the other two joint probabilities to get the marginal of shellfish not contaminated, or we could take 1 minus 0.12, the complement, and either way we would get 0.88. I encourage you to work through your math to stop the video to make sure you are following along. So we can now fill in the numbers that we just calculated for the marginal probability that shellfish are contaminated, that's 0.12, and shellfish not contaminated, 0.88. And again, the problem asks about the new conditional probability that we're trying to calculate, which is given shellfish are contaminated, what's the chance that fib exceeds the standard? And so this is the probability that we're calculating. And we also know one other piece of information, and that is the joint of 0.075. We got that from the previous probability tree, remembering that probability of A and B equals a probability of B and A. So now we have all the probabilities that we need, and we can use the multiplication rule to solve for this conditional probability. Remembering that the marginal times the conditional equals the joint, and therefore the conditional equals the joint divided by the marginal. So please go ahead and stop the video and calculate out that conditional probability to solve the problem. So again, remember the joint probability equals marginal times the conditional, or rearrange the conditional equals the joint divided by the marginal. Therefore, the probability that fib exceeds the standard given shellfish contaminated equals the probability that fib exceeds the standard and shellfish contaminated divided by the probability that shellfish is contaminated. This is equal to 0.075, which is the joint, divided by 0.12, or the marginal, and we get 0.625. So to summarize, given the assumptions of the problem, if shellfish are found to be contaminated, there is a 62.5% chance that they come from an estuary that exceeds the FIB state standard. So in essence, what we did through probability tree manipulation was use Bayes' theorem intuitively. Here is Bayes' theorem: probability A given B equals probability of B given A times probability A. The conditional times the marginal is equivalent to the joint probability A and B. And then on the denominator we have that again, probability B given A times probability A, plus the probability B given not A times probability of not A. That's the joint probability of not A and B. So what I would like you to do is use this formula to solve the same problem. Fill in those probabilities that were given in the problem and see if you come up with the same answer. Again, the answer or the solution was 0.625. I would like to close this video with a practice problem. Please solve this problem through both probability tree manipulation and the use of Bayes' theorem. I will post the solution. After studying the geology of a region in southwest Texas, we determined that there is a 40% chance that a prospect field will produce oil. Also, if oil is present in the field, there is an 80% chance that a specific well will strike oil. Assume that if there is no oil in the field, there will be no oil in the well. If we drill one well and it comes up dry, no oil, what is the probability that the prospect field has oil? Again, please walk through the steps that we went through, identify the key probabilities in the problem, sketch out a probability tree, manipulate or flip the tree, and solve for the conditional probability. Please also solve by using Bayes' theorem. Again, I will post the solution. To recap, in this video I went over joint, marginal, and conditional probabilities, probability trees and how to manipulate trees and flip a tree to switch the conditionalities, as well as Bayes' theorem. Thank you very much for joining in.